All right, so I'm going to make a video that talks about basically most of the concepts for this unit of relations. There's a lot of review stuff. The most challenging part is the word problems, and so some strategies on that will be left till later. This is just the basics. So first question we have is, what are relations? Relations are when you have two variables that are related. Most of the time this is going to be done with an equation, but we can also represent those in a couple of ways like table of values and graphs. So, for example, if I have like the number of chickens that I have at my house, okay, and my age, those are two variables, but they're not related. They are not a relation. But if I said something like my age and my height, those two are variables. They're things that are different at different points, but they are related. As my age increases, my height will also increase, right? So because those are relations, we could write an equation that would show how they're connected, and we could also show it on a graph, kind of showing what's happened as my age goes up, my height, and then decrease a bit at the end, you know, when we get older. Same kind of idea. That's a relation. Most of the stuff we're dealing with isn't going to say, is it a relation or not? You're just going to have to deal with the patterns. So, and a really important part is figuring out dependent and independent variables. So in the example we just gave, age and height, one of them is dependent, one of them is independent. There's always one and the other. The independent variable happens no matter what. The dependent variable changes based on the independent variable. So in this situation here, the age is the independent variable because my age is going to keep going up no matter what. It changes by itself. The height is going to change based on my age. So it's going to be the dependent variable. The other way that you can think of it is one of these is as if you had like a calculator. Which information do you put in and which is going to be the answer that is put out? So if I needed to calculate, you would say, well, if I give the computer my age, it will be able to tell him my height. This analogy isn't perfect, but it's like an idea to help us understand, and it's going to be helpful when we do functions later. Okay, so we have input and output. Let's do another example, gas versus distance. So the idea is this is the amount of gas in my car, and this is how far I drive. So is it the gas will cause distance to happen, or the distance causes gas to change? And it's going to be that way. Okay, the distance is going to be the input, and the output is going to be the gas that's remaining. So that means that the distance is the independent and the gas is the dependent. Another trick you can decide is independent variables if there's time in the question. Okay, so like hours, age, number of days, whatever, there's almost always the independent because time happens no matter what you do. It's always going to pass. Whatever question has, or whatever variable has total in it, so like if you're doing something like total amount of money, or total amount of trees, or total amount of chicken, that is almost always the dependent because you calculate the total based on some information. Again, not always true, but almost always true. Now, when you have situations, you're able to create a table of values, which is a way you can see a bunch of information at once. So let's say that for this gas question, I got an equation. Let's say it was this. We'll say the amount of gas I have left is equal to negative 10d plus 100. Let's say that's my equation. Okay? If I wanted to make a table of values, it looks like this. It's a big T chart. You're always going to put your independent variable here, and your dependent variable on this side. So in this situation, we said that the gas was the dependent variable and the distance was the independent. So I'm going to put here and here. Honestly, I think it's a lot easier to put X and Y because then it's easy to see the order, but whatever, we're using those variables. When you throw in your table of values using an equation, you're actually going to just put numbers that make sense. So you usually start with 0 and then put other numbers that are going to work and show you what's going on. So like 1, 2, 3, whatever. Some situations you have to put some negatives, but in our situation we just have to think, well, can we have like a negative distance? No, I don't really think so. I guess backwards, but no. So we wouldn't have negative values. So I'm going to sub my numbers in the equation and get my answers. So the first one is 0. So I'm going to sub 0 in for D. So G equals negative 10. And then 0 for D plus 100. So when I do that math, it gives me 100. So the first G is 100. When I sub in 1 instead, I'll put the 1 here. That's going to give me negative 10 plus 100, which is 90. It's 90. And if you continue the pattern, you'll see 80, 70, etc., blah, blah, blah. Okay? So now, using your table of values, you're actually able to form a graph. So let's make our graph. The independent variable is always going to go here, and the dependent variable is always going to go here. So our independent variable was the distance, and our dependent variable was the gas left. Make sure you use units, so it's liters, kilometers, whatever the question says. So now we can put these onto our graph. Each pair is a point on our graph. I'm going to make our scale be that 10, 20, 30, 40, that's 50, 70, 80, 90, that's 100. Same idea here, 0, 1, 2, 3, 4, 5, 10. Oh, sorry. 100, 50, 5, 10. Cool. Okay, so when we put this in, we can put our numbers. So 0, 100 means that after 0 distance, my point's going to go right there. Let's make it easier to see. That's the first point right there. The second one is 190, so I'm going to go to 1 and then go up to 90 and put a point. And then 280, I'm going to go to 2 on my x-axis and 80 on my y-axis and put a point. There we go. And then now we can start to see the pattern, right? So you can take a ruler, draw a straight line connecting them, and that shows you the pattern of what's going on. You have to be careful. Sometimes you can't actually draw a line. You can see the pattern, but you might not be able to draw a line. It depends on if there's decimals. So in this case situation, can you have a decimal of a kilometer? Yes. Can you have a decimal of liters? Yes. So we would have a solid line. If it was something like puppies, okay, you can't have half a puppy. That's gross. So you wouldn't be able to connect it as a straight line to show all those points in between are part of the pattern. So we now have a graph, which we did based on our table of values, which we did based on our equation. However, there's some questions which I think are actually pretty tough where you have to actually write an equation. So for example, let's say we had a pattern. Okay, it'll be like this. Let's just make it easier. Okay, so this is our pattern, and we need to write a relation that's going to show the difference between our two variables. The first thing we need to figure out are what are our variables. So number one, the figure number. That is going to be a variable. So it says 1, 2, 3. Okay. The other variable could be different in different situations. This is going to be number of squares. So we need to decide which one depends on the other. So in this situation, the figure number is going 1, 2, 3, kind of no matter what. The next one's going to be 4. The number of squares changes based on which figure it is. So that means the figure number is the x, the independent, and the number of squares is the y, the dependent. So we now can write an equation. Our equations are always going to work the same basic way. Let's do this. It's always going to be y equals. We always put the dependent here. And then there's going to be x with some stuff happening. The stuff depends on what the pattern is, but the most common pattern you're going to see is a linear pattern, which basically is showing what's the change. So as we go between patterns, as we go between figures, we can see, well, every time I'm adding 2 squares, adding 2 squares. That's the change amount. And the change is happening every figure, per figure. So whatever that change number is, we're actually going to put right here. That's the change amount. Because basically, let's say we went to figure 100. We would have to do the change 100 times. So we would have to do 2 times 100. Now the thing that a lot of students miss is the number here. This is the initial value. This is what did we have at the start. So if we think of our gas situation, the initial value was up here. It's how much gas we had at the start. It was 100. And that's why in our equation it said plus 100. In this situation, it's what's the amount going to be actually at figure 0, because that's the start. A lot of students mess up and think figure 1 is the start. In math, we start from 0. So in figure 0, if we look at the pattern, there's actually going to be just one little square, which then fits because this would be +2 every time. So in this situation, my initial value is going to be +1 because we had one single square in our first figure 0. So this is our equation. Y equals 2x, that was the change amount, +1. There will be different equations, and some of them you have to figure out based on the word problem, but a lot of them are going to follow this simple pattern. Now that you have an equation, I could make a table of values if I wanted, and I could make a graph, but I'm not going to do that because we already did that. Now, the last thing that we need to talk about is x-intercepts and y-intercepts. I call zint and yint, okay? In different situations, they're going to be obviously different, but you need to understand what they mean in the context of word problems and how to calculate them. So this is my equation. I could, if I wanted, make a table of values and then sub in numbers to find all the values, and then I could graph it, but I'm lazy. I want to find the x-intercept and y-intercept in a second. So let's just zoom back to this past graph we did over here, okay? When we look at this, there are two spots we care about. This is the y-intercept up here. This is the x-intercept down here. You'll notice something special. At this point, the coordinates are, for the x value, 0. For the y value, it's going to be different in every graph. But no matter where our line crosses, if it's this line, if it's this line, no matter where it crosses, the x value for all of these is always going to be 0. The spot where the line crosses this x-axis or this y-axis right there is always 0. We can use that to our advantage. Here, wherever our line crosses the x-axis, the reverse is true. In this situation, I don't know what the x is necessarily, it's kind of hard to see, but the y value is 0. So this is a little backwards, but the y-intercept has an x value of 0, which makes sense if you look at a graph. And the x-intercept has a y value of 0. So let's go back to here, to our question. Okay, we have a paper plane that's crashing. Y is the height, x is the time, let's say. Okay, so in a question like this, it's going to say, what is the x and y-intercept? So we know for the y-intercept, x is equal to 0. So I'm going to sub x equals 0 into the equation. So I got y is equal to -2, 0 plus 10. So y is equal to 10. So I cancel that. The other way you can see it is it's just the constant there. Be careful though, because some questions are a little more difficult or don't have a constant, in which case it's more complicated. But we can just sub in 0 and it will always work every time. If you sub in x equals 0, it will give you the y-intercept. So on my graph, I know that this point is going to be, that's the y-intercept. Now, the x-intercept was the reverse. For the x-intercept, we knew that y is equal to 0, so I'm going to sub that in. So this is going to be 0 equals -2x plus 10. So I'm going to rearrange and solve. You're going to get -10 equals -2x. Divide by 2, -2 is going to give me x equals to 5. So on my graph, I'm going to put a point right there. That's my x-intercept. And now you'll notice you had 2 points. So if I really wanted on my graph, I could connect those two with a line. Because again, this was time, which has fractions, and this was height, which also has fractions. So that shows my pattern. Now, I want you to just think for a sec. What do these represent in the word problem? We have a paper plane and it's crashing. This represents when the height is 0, which if there's a paper plane crashing when the height is 0, that's when it hits the ground. Now, not every word problem is about paper planes crashing, but the x and the y-intercepts are usually special points in the graph. They have something that matters. In this situation, we have time. This is the height when time equals 0. Time equals 0 means the start. Like if the start of a race or right when I threw it or whatever's going on, those are the 2 points. And those actually are significant to me. So what we can say is at the start, the height was 10. That means the paper plane was thrown from a height of 10 meters or whatever. In this situation, the ground was at x equals 5, which is the time, right? So that means the plane hits the ground after 5 seconds. So using those 2 points, which are pretty easy to calculate, x equals 0, y equals 0, we're able to find really important values for these graphs. And just so you know, even if you have a weird equation, okay, you can still sub in x equals 0 or y equals 0 into this to find the x and y intercepts. It'll still work even if you have a weird graph that's like curvy. So those are the basic concepts of this unit. It was a long video, but that's all we're going to cover over a series of lessons.